Okay, kids, we're back today and we're talking about the motor principle. Now, it's very important that you watch the video beforehand or this is going to kind of be difficult to follow. The motor principle, what's it all about? It's about when magnetic fields interact with each other. In particular, when you've got a magnetic field that's from a ferromagnetic field in red. All right, here it is. So we've got what we call here a horseshoe magnet. All right, it's a bar magnet that's kind of been bent around like this, like a horseshoe. And here's the side view. And in red, I've drawn the magnetic field that would go from north to south. Magnetic field lines always go from the north seeking pole to the south seeking pole. And this is the top view, as if I'm looking down at it. And still, magnetic fields go from north to south seeking pole. So there's the red magnetic field from the ferromagnet. Now, what do I have in between the north and the south seeking pole? Well, there's a wire here. There's the wire here, and it's got a current moving in it. Here's that same wire drawn from the side view. You're seeing it on its end, and the current with the X there means it's going into the page. What else have I drawn? Well, in green, I've drawn the electromagnetic magnetic field, the magnetic field that is created because there's a current in this wire here. And we're going to use our right hand rule, and we're going to point our thumb in the direction of this current. So our thumb's pointing to the right, and we'll get a clockwise circular magnetic field around this wire. Same thing here if we look at it from the side view. Now our thumb is pointing into the screen, into the page. And with our thumb pointing into the page, our fingertips curl as if you're holding an ice cream cone, right? Your thumb is into the page and your fingers are curled as if they're holding something. And look, they curl in a clockwise direction. Well, these two magnetic fields are going to interact with each other. And they're going to interact with each other to produce a force on each other. And there'll be a force on this wire. There'll be a force on this wire. And this wire will move downward as these two uh, magnetic fields interact with each other. Now, you've seen interaction of magnetic fields before. Look, you got two bar magnets, okay? So here, north seeking pole at the top, north seeking pole at the top, right? Magnetic field line leaves the north, goes into the south. Magnetic field line leaves the north, goes into the south. These two magnetic fields are in the same direction. When you have magnetic fields in the same direction, there is a repulsion. So these two would repel away from each other. Similarly, if you have a wire with a current out of the page, and now we're going to point our thumb out of the page for that one. So we definitely have a counterclockwise magnetic field, right? Look how this goes against the spin of a clock. That's a counterclockwise magnetic field here. Here the current is going into the page, so we point our thumb into the page, and we definitely have a circular magnetic field from that wire that's clockwise. And look at these two magnetic fields. They're in the same direction, just like these two are in the same direction. And you get repulsion. They push each other apart. Well, if you take a look here, look, these are in the same direction. So this wire is going to be pushed away from where the magnetic fields are in the same direction. That's why it was pushed down. And this can all be uh, described in what we call the right-hand rule for the motor principle. So here's our example. Here's a north-seeking pole, here's a south-seeking pole. And the magnetic field goes from north to south. And here is a wire with the current coming out of the page. So you're going to find the magnetic field of that wire by pointing your thumb out of the page, out of the screen. And the magnetic field is here is definitely counterclockwise. It goes against the spin of the clock. All right? Well, you probably notice here that the magnetic field down here from the wire and the electromagnetic field and the magnetic field here from the north and south seeking poles of the material, the ferromagnetic magnetic field. Here they're in the same direction, so we're going to have repulsion away from it, and this wire would feel a force upward. So how do we figure that out? Well, you use an open right hand, so you keep your right hand flat and open. There's a picture in the textbook. And what you do is you point your thumb in the direction of the current. So our thumb is going to point out of the screen. And you point your fingertips in the direction of the external magnetic field, which runs from north to south, which is pointing from, in this situation, left to right. So your fingertips are going to point to the right. So with your right hand's thumb pointing out of the screen and your open-handed fingers pointing to the right, you will notice that your palm points upward. So the palm points in the direction of the force on the current carrying conductor. I've written that in black. So really you can use this right hand rule for the motor principle. Thumb points in the direction of the current out of the screen. Fingertips point in the direction of the external magnetic field. In this case, they point to the right, always north to south. Your palm is forced to be up the screen or up the page, upward, and that'll be the direction of the force on that conductor. The other way you can look at it is remember that wherever magnetic field lines are in the same direction, it's going to be repelled away from there. And this is the motor principle. So I had you watch the video. I have some other links that that are on today's announcement. You're going to do some reading, answer some questions, and we'll move forward. Make sure you use all the resources that I put in every lesson, please. Not just my video lesson, not just the video I include, but there's other little tidbits I put in there. Okay, thanks and have a great day.